So in today's lecture we are going to talk about torsion. The torque, the quantity, the physical quantity torque is something you are already familiar with. So it is, you know that it is essentially the equivalent of force in rotational motion. So let's just start with a very simple problem. If you have okay, before talking about torsion, if you have a bar on which you are applying force, which is being subjected to a force F1, a tensile force F1, what is the internal force in this bar at any point? That will be F1. And let's say you have another bar here which is subjected to force F1 F2 and F1 plus F2 here. So you can see that both of these bars are in equilibrium. What is the condition of equilibrium? For this to be in equilibrium, net force in any direction should be 0. What is the net force in x direction here, or the horizontal direction here? So that is F1 minus F1, 0. And here, what is the net force in x direction? So you have towards right F1 plus F2, and F2 towards left and F1 towards left. Sum is 0. So for advanced strength of materials, for in this particular course we are not going to talk a lot about motions. So you will see that we will be dealing with materials which are under force or torque, and they will essentially be in equilibrium. So if I ask the same question here, what will be the internal force resultant at this part of the bar? What is the internal force resultant at this part of the bar? How do you find that out? To find internal force resultant at this part, you cut the bar at this part and take it out. So I've cut the bar here and I've taken it out. I have force F1 here, and internal force resultant essentially mean that that force will be equal to the net force that should be applied here. And what should be that force? What should be force F, which must be applied here? Net force in x direction is equal to 0. F minus F1 should be 0, means F is equal to F1. So the internal force resultant here, F, will be equal to F1. And what is the internal force resultant here? For that you can cut the bar here and take out this part or this part. So if you take the right side part, you get so this is the right side, and on the right side you have F1 plus F2, and on the left side here you have the internal force resultant which you need to calculate. And again, using the equations of equilibrium in x direction, F1 plus F2, and F is towards left, minus F should be equal to 0, which means that F is equal to F1 plus F2. So the internal force resultant here is F1 plus F2, and internal force resultant here is F1, which we have already found out. And what if we take the left side part, this part? So if I take that part, you have F1 here and F2 here, F2 here, and again you will find out that the internal force resultant here is F is equal to F1 plus F2. So simply, just like the previous case, you just apply the equations of equilibrium. That's how you need to find out the internal force resultant. If you want to find out internal force resultant at any point, cut the bar at that point, use the equations of equilibrium, find out the force that should have been there to make the whole system in equilibrium, or the part of selected in equilibrium, and that force is called internal force resultant. And the direction of internal force resultant, that's something that is something that should be either here in this case, that should be either tensile or compressive. And that depends on the magnitude of F1 and F2, etc. So you may have seen that when I took the right side part, I got F towards left, and when I took the left side part, I got the internal force resultant towards right. And that seems contradictory, but that's completely okay, because internal force resultant means when I cut this part out, to make the right side, the left side of the part is pulling the right side towards left, and the right side part is pulling the left side towards right to make it in equilibrium. So that's what the internal materials of this bar is doing there. So it's if it's a steel bar, it's steel molecules acts like a gum which holds these two parts together. So if you think it like that, so you'll realize that these two parts are trying to pull each other in their own direction, and that will be opposite to each other. So similarly, torsion. What is torque? Torque, like I told you, it's the moment of force, and you know that. So how do we show the magnitude of the I think you use the right hand thumb rule to find out the direction of torque. So if you just a second, I'll just I think I can show you some multimedia here. So this particular picture here, if you look at it, you can see that so when you apply torque, torque is essentially the moment of force, and if you try to rotate this particular bar which is fixed on other side, so you will be sort of applying a force in the direction of your curled fingers, and torque is said to have the direction which is shown by your thumb. So that is the right hand thumb rule. It's called the right hand thumb rule because you are using the right hand. So here the word force is written because we are applying a force to get the torque. Torque is the moment of force, and you need to, when you try to rotate a bar, you are essentially trying to apply a force. You are trying to apply a couple, that's a better term. So you are trying to rotate it, and you can think it in two ways. The force you are trying to apply is in the direction of your curled fingers, or the bar will rotate in the direction of the curled fingers. In that case, the torque will have the direction of the thumb. So this is called the right hand thumb rule. So now if I draw a bar here, and so I can use I can show the direction here. Let's just say I'm applying a torque 10 Newton meter in this direction, and 10 Newton meter in this direction. So what is the internal torque resultant in the middle of the bar? And that will be T is equal to 10 Newton meter. So this is just like the force. Here instead of the force, torque is being applied, and you can find out the internal torque resultant just the way you find out internal force resultant. So if you have so a better figure will be this one. So you have a shaft here ABC, and you are applying a torque here, here and here. So you have a torque 20 Newton meter here, 10 Newton meter here, and 30 Newton meter here. Now let's say you have to find out the internal torque resultant at cross section K. So what do? You cut the part here, and so if you use the right hand thumb rule, you know that the torque has direction, this direction here and this direction here. So here, if you assume the direction of torque to be this, and we call it T, then T, internal torque resultant T, is equal to, now I'd rather use net torque in x direction is equal to 0, which means that minus t is towards left, that's why I'm taking negative, plus 10 minus 30 is equal to 0. That means that T is equal to 10 minus 30 is equal to minus 20. So this is the internal torque here. So it has a negative value, which means that the direction we have assumed is wrong, and it has the direction other way around. But I think in most cases we need to worry about only the magnitude. So the magnitude of torque here is 20. So you will get the same thing if you take the other part. Here you have the internal, if you use the right hand thumb rule, you'll see that this is the direction of torque here, 20 Newton meter. And if you assume the torque, internal torque here as something called T. Why am I using T here? This T is okay. Let's call this one T1. No, it's not good. Okay, we assume it to be T, and net force in x direction is 0, net torque in x direction is 0. That means that T plus 20 is equal to 0, which means that T is equal to minus 20. The same thing, so this assumed direction is wrong. It should be the other way around. So obviously the torque here and torque here, they'll have opposite direction, because this part is applying a torque on this part and this part is applying a torque on this part. So these are Newton's action reaction pairs. So they will be equal in magnitude and opposite in direction. Equal in magnitude, opposite in direction. That's why you get direction opposite here and here. So that's about that's how you calculate internal torque resultant in shafts.